Although the destruction of the Tay Bridge had stopped Booch in his tracks, people and goods still needed to cross the firths. For many hundreds of years, people had crossed the Firth of Forth using ferries. It was all well and good, but modernisation was slowly encroaching and a better link was needed to move the precious cargo. Booch had previously proposed a suspension bridge designed for crossing the Firth of Forth, but everyone had lost confidence in the engineer. Almost overnight, work on his design was stopped as the plans were reassessed. Luckily, the work had only consisted of a brick pier at the western end of the bridge. The Board of Trade, in the wake of the inquiry, announced that all bridges must be designed with a tolerance of a lateral wind load no less than 56 pounds per square foot. Booch's suspension bridge fell substantially below the minimum requirement. If it had been built to Booch's specifications, the bridge would have fallen in a moderate storm, never mind a large one. Booch's design was formally abandoned in early 1881, and it was decided that the design should not be in the hands of just one engineer. So they consulted Sir John Fowler, Thomas Harrison and Sir Benjamin Baker to spearhead the new bridge. Booch's unfinished pier was left in situ as it would be unaffected by the men's plans. Sir John Fowler had engineering in his blood. His father was a land surveyor, and Sir John was brought into the engineering trade the moment he left school. After his apprenticeship was complete, Sir John worked for many different railways, including the Furness Railway and the London and Brighton Railway. He was in the centre of the railway boom, so openings for engineers were plentiful. His highly skilled work and craftsmanship saw him as the resident engineer of the Stockton and Darlington Railway at just 24 years old, making him one of the youngest resident engineers of the era. It wasn't a long tenure, however, as demand for his services and expertise led him to London in 1844. By the time John turned 35, he was a member of the Institution of Mechanical Engineers and a member of the Institution of Civil Engineers, putting him easily with the likes of Stephenson and Brunel. John established a very busy independent engineering practice and would be called upon to give advice on many of the grand plans all over the country. One of the most ambitious was the London Underground Metropolitan Railway. He helped devise the cut and cover method to build lines underground and was the main go-to man for any large railway project. Sir John was also not a stranger to bridges. He had designed some of the most iconic bridges. Some are still in use today. The old Grosvenor Bridge, the first bridge to cut across the Thames, and the Dollysbrook Viaduct. The Grosvenor Bridge has been modified and changed over the years to accommodate more tracks and electrification, but the viaduct structurally remains virtually untouched since the day it was finished. Sir Benjamin Baker, ironically, was well aware of the failings of the Tay Bridge and why it had fallen. In fact, he was called upon by Sir Thomas Booch himself as a key witness to help defend him. Sir Benjamin gave evidence that the bridge was not blown over in the wind and that wind stresses on the Tay was not an unusual level that night. The argument was rejected in the inquiry. However, he did manage to prove that the meteorologists were overestimating wind pressure that night later in the Forth Bridge's construction and in its testing. Before being selected for the Forth Bridge project, Benjamin was a big advocate for steel bridges and showed how larger spans were possible using steel rather than cast iron as a medium. Both him and Sir John Fowler had worked closely together on various large projects, and both were a perfect choice to help design and build the bridge. Both men knew how each other worked, and they made a formidable team. Thomas Elliott Harrison's move into engineering was not as smooth as Benjamin's and John's, and he spent a year as an accountant's assistant. He got his big break when Robert Stephenson employed him to help design plans for a new section of line for Wolverhampton to Rugby. From these humble beginnings, he proved himself and found himself on bigger and larger projects. When George Stephenson retired as chief engineer of the York, Newcastle and Berwick Railway, it was Thomas that filled the boots and was briefly promoted to general manager, to help provision and oversee a merger with the Leeds Northern Railway. The result was the North Eastern Railway, one of the largest powerhouses in the north. It was while in this job he was offered to help design the Forth Bridge and had helped start the project. However, tragically, he sadly passed away before he saw the project come to any fruition. Benjamin knew the future lay in steel and wanted to incorporate it in its new design, but he couldn't risk making the same mistakes as Booch. He also didn't want to use any radical principles. Rather than a suspension bridge, he settled on a cantilever design. A cantilever is a structure that projects horizontally into a space and is supported by only one end, which acts as an anchor. Benjamin wanted to use a suspended span cantilever. In this now famous photo, the principle of the bridge is laid out. The weights act as anchors, and the wooden bars and the outstretched arms of the men shows how the weight of the man in the middle, identified as Keiichi Wantabe, was able to be transferred to the anchors. The upper arms were stretched in tension, while the lower arms were squeezed in compression, thus forming a perfect balance. Before work on the actual bridge could begin, work started on either end of the banks. Wooden huts to house the workers, workshops and shops were erected. A cable was laid across the span so that the foreman and supervisors could speak directly by telephone. A sawmill and cement store was put in place, and railway sidings were built ready to handle the masses of steel and provisions. Old buildings were removed, including a lifeboat house and fortifications. On the island of Inchgarvie, the rock was cut down and a seawall was erected. The old castle-style buildings were re-roofed and were used for offices and a place for the workers to sleep. Each cantilever would be seated on 4 circular piers. Like the Tay Bridge, each one would need to be excavated and constructed below or near the sea level. Where the foundation was below the waterline, a caisson was used. 6 of the caissons were built off-site and then rebuilt at South Queensferry. They were then floated into position and then sunk down. Each foundation was unique to suit the different sites, but the top was a tapered granite pier, each with a diameter of 55 feet. Different methods were used depending on the conditions. On the island of Inchgarvie, the rock was blasted and cut. At South Queensferry, a caisson was accidentally tilted due to an exceptionally low tide. When the tide rose, the caisson remained in its tilt, embedded in the mud, causing water to flood it. The water caused the caisson to tilt further as the tide ebbed. Divers tried to save the caisson by bolting plates to try and lift the caisson up, and the water was pumped away. But the water was removed too quickly and the water pressure tore a hole in the wall. Rather than scrap the caisson was reinforced with timber, and although it set the project back 10 or so months, it was finally free of the mud and put into position. Now that the caissons were in place, the work on the twin approach viaducts could begin. It was decided to build the viaducts at low level and then raise them into position using timbers. Each span was connected to make a continuous girder, separated only by an expansion joint. Each of the 30 spans weighed in at over 200 tons apiece, giving the bridge much needed anchorage. Once both viaducts were ready, the last and most important phase could start, the cantilevers. The workshops on the hill at South Queensferry started to bend the steel needed into the required shape. The whole centrepiece went together like a careful jigsaw puzzle. Each piece was carefully moulded and rivet holes cut. Each piece was labelled and cranes would lift each piece into position, then hydraulic riveters would then secure each piece down. At its peak, over 4,600 people worked on the bridge, but it was not without cost. At first, 57 people were reported to have died in the bridge's construction, but after checking historical records, it was found that this number was inaccurate, as it didn't include those that had passed building the viaducts. In 2019, another 21 deaths were uncovered as part of an apparent cover-up. This meant that more people died building the Forth Bridge than that were lost in the Tay. The bridge was completed in 1889, but it couldn't be open to the public yet. Testing had to prove that the bridge was safe. The bridge was tested with more than twice its load it was designed for, and the bridge performed very well. It was also noted that several large storms had hit the bridge, and unlike the Tay, the movement of the bridge had been noted at just 25 millimetres. On the 4th of March 1890, the Duke of Rothesay was given a golden rivet in a dazzling ceremony. The rivet was inscribed, and he drove it home to great fanfare. The bridge was now the largest cantilever bridge in the world and ready to take its first passengers. But was it really? True, there was now a bridge, but the lines to and from it were now inadequate. So even though the bridge was completed in the December, it took a good 6 months for the lines to be updated to take express services. The new fourth bridge, though, was a game changer. Almost overnight, it had taken a 13-hour journey from London to Aberdeen and sliced it to a mere 8 hours. The North British Railway had won the Great Race of the North, and many major players from the south, such as the Midland Railway and the Great Northern Railway, had rights to use the bridge. In exchange, the bridge's cost was shared between them. By the time of the grouping, the bridge was jointly owned by 4 companies and was owned in part by the LMS and the LNER. There is a popular myth that the bridge is constantly needing to be painted, and when the painting's done, it's time to start again. While this is a folk tale, there is a permanent maintenance crew ready to do any repairs needed. In 2011, a thorough and entire repaint was granted. The old paint was stripped away and any defects repaired. The new paint is expected to last about 25 years, and is estimated that with regular maintenance, that the bridge will last easily in excess of 100. I have never covered a UNESCO heritage site before, but this bridge is clearly something special. I had planned to cover this topic for some time, but never thought it would take me on a journey such as this. I was extremely lucky to travel on this bridge during my stay in Edinburgh in 2012, and its structure is something else. The fourth bridge takes my breath away, and it still remains the largest cantilever bridge in Europe. It's amazing to think that this thing was made nearly 150 years ago. To many, it's as modern as the latest bridges being built today.